Welcome to Brain Vision.
Okay, so in this question, we're dealing with the wooden bar on a marimba. And we're told that the frequency of this specific wooden bar is 87.0 hertz. And it is 40 centimeters long. So L equals 40.0 centimeters, which is 0.400 meters. And we're also told that the transverse wave of this vibration in the wooden bar has 3 antinodes and 2 nodes. So if we go ahead and draw a quick diagram, so our wave is going to look like this: 3 antinodes and 2 nodes. So that tells us, if we look at it, we have, starting at the left side, we have an antinode, and then we have the opposite antinode in the middle of the bar, and at the other end, we go back to the original antinode. So that tells us that the length of the bar is equal to the wavelength of the transverse wave. So that's pretty helpful. And from this information, in part A, we want to find out what the speed of the transverse wave is. So that's a pretty straightforward question. We have the frequency and we have the information that we need to find out the wavelength. So we can go ahead and write down that wave speed is equal to frequency times wavelength. And we can go ahead and just plug those in. So frequency is 87 hertz. And the wavelength is 0.400 meters. And we can go ahead and calculate that out. So V is 34.8 meters per second. So that is our answer for part A. And then in part B, we're told that a metal tube is attached to below the wooden bar to help it resonate and to make it louder. And we're supposed to figure out how long this bar, or how long this tube, needs to be if it's open only at the top and closed at the bottom. We need to figure out how long this tube needs to be in order to make it resonate with the marimba bar. So here again, the frequency is going to be 87.0 hertz. So that doesn't change. But now we're dealing with sound waves in air. So the speed of the wave is going to be 343 meters per second. And then we're also told that the tube needs to be close to the bottom and open at the top. So if we draw a quick diagram of that, it's also going to resonate most strongly if it's resonating at the fundamental frequency and not at a harmonic. So we know that we're looking at the fundamental frequency, which means that there's going to be a node at the bottom and then an antinode at the top and nothing in between. So that tells us that the length of the tube is going to be equal to lambda over 4, because we go from a node to an antinode, with the whole length of the tube. If we double that, we get back to a node. But if we triple that, we go to the opposite antinode, and if we quadruple the length of the tube, then we finally reach a full wavelength. So our length of the bar is going to be equal to 1/4 of the wavelength. So we're trying to find the length of the bar. So what we can do is we have the equation that lambda is going to be equal to wave speed over frequency. And we know that the length of the tube is going to be 1/4 the wavelength. So we can say that L is equal to V over 4. Oh, not 4. 4. There we go. Sorry. I wrote an F a little early. So we can say that L is going to be equal to V over 4F, because that is going to be 1/4 the wavelength. We have V and we have F, so we can go ahead and just plug that in. So V, of course, 343 divided by 4 times 87.0. And if you plug that in, you should get that the length of the tube needs to be 0.986 meters. And that's our answer for part B, and we are all done.